What is up, young chemists? Mr. Rosen here. Today we are talking about percent composition and empirical formulas and molecular formulas. It's kind of two separate things, but we had these in the same lesson packet, at least in my classroom. But we'll start with percent composition. The name kind of implies what we're doing here. If you have a compound, the compound is made of multiple elements, and percent composition is simply breaking down what percent of the compound's mass is contributed by each particular element. Okay, so you could read this here. It's just basically saying that the percent composition is the percent of the compound's total mass that's contributed by that element, right? And to do this, to find out what the percent composition is, all you really need to know is how much the whole thing weighs, which is what's called the molar mass, and then you divide the mass contributed by each element by the molar mass, and then turn it into a percentage. So these are pretty easy problems. This says, what's the percent composition of AgNO3? So thinking about it another way, we're wondering, how much of this compound's mass is contributed by Ag? How much of this compound's mass is contributed by nitrogen? And how much of this compound's mass is contributed by oxygen? So the first question is, well, how much does the whole thing weigh? That is, what's the molar mass of the substance? So on the periodic table, Ag is 107.87 grams per mole. Nitrogen is 14.01 grams per mole. And oxygen is 16 grams per mole. Now, it's important to remember that there are 3 oxygens, so 16 times 3 gives us 48. Now we're going to add all 3 of these together. Okay, we're going to add them all together. And when we do that, bring over the calculator here, 107.87 plus 14.01 plus 48, we get 169.88. That's our molar mass, 169.88 grams per mole. So that's how much the whole thing weighs. So if you had a mole of it, it would be 169.88 grams. Now, of that mass, what percentage of that mass comes from silver? What percent comes from nitrogen? What percent comes from oxygen? That's what we're going to be finding out. That's what percent composition is all about. So next, what you have to do is take the mass contributed to the total by each element and divide it by the molar mass of the whole thing. So for Ag, 107.87 of the 169.88 came from the silver. So if we take the mass contributed by the silver, divided by the mass of the whole thing, we get a number which is going to be less than 1. If we take 107.87 and divide it by that number, we get 0.6, I'll just write out 0.63498. Okay, but we want percent composition, so we're going to take this times 100, and that gives us 63. We'll say 50% Ag by mass. So it's about 63%, 63.5% silver by mass. Now we're going to do the same thing with the other elements. Nitrogen is 14.01 grams out of the 169.88 grams, which again, it's going to give us a number less than 1, 14.01 divided by 169.88. We get 0.08 2470 times 100 is 8.2 8.247% nitrogen. Now, just sort of by subtraction, these are, because there's 3 elements, those 3 elements are going to make up 100% of the mass. So if you took 100 and you minus these numbers, what's left is going to be what's contributed by oxygen. But we're going to write it out just because. Now remember, oxygen has a mass of 16. I'm not going to put 16 on top here. I'm going to put 48 on top here because there were 3 oxygens. So I know we only had 1 silver and we only had 1 nitrogen, but we have 3 oxygens. So that's a way that students mess this up, is they just put the molar mass of oxygen. But you have to put how, there are 3 oxygens. So it contributed 48 of the 169.88. So we have to include that. That's going to give us 0.28255 times 100. I'm just moving the decimal over a couple places. 28.26% oxygen. Right. Now, if we want to, we could add these together to check our work. So if I did 63.5 plus 8.247 plus 28.26, I get that number, which if you look at it, it's, sorry, I have a little bit of a glare here, but 100.007, so it's very, very close to 100. Obviously, I got to round these numbers at some point. I basically just kept them all to 4 significant figures, but you should get 100 or very close to 100. Often with rounding, it says 99.999 or 100.00 something. So it should be 100 or very close to 100, just depending on your rounding. Right. So this is a breakdown of what percent of AgNO3's mass comes from each element. Right. And that's kind of just what it says here. Step 3 is take each answer and multiply by 100. We did that. All right, and these values represent the percent composition for AgNO3. So this is percent composition. Now, often you don't have to, if you're doing practice problems, maybe they have you solve for all 3, but usually in a test problem, it'll say, what is the percent of, percent by mass of nitrogen in AgNO3, and you just solve for one of the elements. But if you can, solve for all of them, obviously you can solve for one. So we're going to do a couple more percent composition problems. These are, again, pretty easy, but, if you're, reviewing, maybe it's been a while, so it's good practice. Caffeine has a chemical formula C8H10N4O2. What's the percent composition of caffeine? So first thing is we need to know what is the molar mass of caffeine, right? How much does this whole thing weigh? So we have 8 carbons, so 12.01 times 8. That's 8 carbons. We have 10 hydrogens, so that's 1.01 times 10. We have 4 nitrogens, so that's 14.01 times 4. And then we have 2 oxygens, okay? Oxygen is 16, and we have 2 of them. So the molar mass is 194.22 grams per mole. This is our molar mass of caffeine. So now we're going to break down each element, okay? And maybe I'll just do this as a, grid because we're going to have 4 things. So carbon, right? Carbon is going to be, carbon is 12.01, and we have 8 of them. So 96 a little over 96, right, 96.08 of the grams is contributed by carbon of the 194.22. This is going to be times 100. So this number divided by the total mass is some number times 100. Pretty close to 50%. Okay, so that's 49.47% carbon by mass. So a little bit less than 50% of the mass comes from carbon. Hydrogen is going to be 1.01 times 10 is 10.1. So that's 10.1 grams of the 194.22 grams times 100. So on here, divided by 194.22 times 100, about 5.2%. So a little over 5% hydrogen by mass. We're going to do the same thing for the other elements. So we also have nitrogen. Nitrogen is going to equal 14.01 is nitrogen, and we have 4 of them. So 56.04 of the 194.22 comes from nitrogen. So that's about 28.85% nitrogen. And then finally we have our last one, which is oxygen. Oxygen is going to be 32 of the 194.22. Because we have 2 oxygens, so 16 times 2 is 32. We get about 16 and a half, pretty close to 16 and a half, 16.48% oxygen by mass. Okay, so that's the breakdown. Okay, just sort of looking at this, this is about 50%. If we added 5.2 to this, we get 21.7, right? 21.7. If you added 21.7 to this, you'd get pretty close to 50%, a little bit more than 50%, and this is a little bit less. So this adds up pretty close to 100%. You can put in your calculator and see exactly what you get. So that's percent composition. There is one more, and I'll go through this a little bit more quickly. Again, we're going to have 4 elements, so I'll just break this into quartiles. So first thing we have to figure out what the mass of this is. Now the parentheses maybe look a little bit confusing, or if you're confused about how many of each you have. Without this 2 here, that would mean you have 1 nitrogen and 4 hydrogens. But with that little 2 there, it means you have 2 times whatever is in the parentheses. So you actually have 2 nitrogens and 8 hydrogens. So 14.01 is times 2, plus we have 8 hydrogens. That's 1.01 times 8. Okay, so that gives us the mass of this first part. We then have 1 carbon, so that's 12.01, and then 3 oxygens. Oxygen is 16. 16 times 3 is 48, so plus 48. So the molar mass of this whole thing is 96.11 grams per mole. That's our molar mass. So now I'm just going to find the percent composition of each. Nitrogen is going to be 28.02 over 96.11 times 100, right, because there's 2 nitrogens. So 28.02 divided by, sorry about the siren, It's about 29% nitrogen in this case. We then have hydrogen, which is 8.08 of the 96.11 because we have 8 hydrogens and each hydrogen is 1.01. So zoom out a little bit. Uh, 8.08 divided by 96.11 times 100. About 8.41% hydrogen. At this point, I think you probably all get the idea here. Carbon is 12.01 grams over 96.11. That's a 6. Sorry about that. Times 100. So about 12% carbon, 12.5% carbon, and then the last one is oxygen. Is going to be 48 of the 96.11 grams times 100. This will tell us our percent oxygen by mass. So plug that in there. 48 divided by 96.11 times 100. It's 49.94. So it's about half oxygen. There's a breakdown of the others. Again, if you take this is pretty close to 30. If you add these two together, you get about 20 plus about 30, you get 50 plus this. These add up to 100. All right, so this is percent composition. I think I kind of definitely did enough practice for that one. It's pretty straightforward. So next we're going to do molecular empirical formulas. We're going to start with empirical formulas, okay? But first we have to talk a little bit about some of the vocab that goes with it. So a molecular formula is just, it's the formula that tells you exactly how many of each type of element you have in a compound, right? So like on our previous problems, this is the molecular formula. It tells you that you have 8 carbons, 10 hydrogens, 4 nitrogens, and 1 oxygen. The empirical formula is the simplest whole number ratio where all of these relative amounts are held the same. So, for caffeine, the empirical formula for caffeine would be C4H5N2O. So you notice that this is 1/2 of this, right? 8, 4, 10, 5, 4, 2, 2, 1. So the relative amounts, the ratio of each is the same, but we've reduced it to the simplest, smallest whole numbers. So this would be the empirical formula, and this is the molecular. You can't read that, but that says molecular. Okay, that's molecular formula. Sorry about that. So I give an example here of glucose, all right? Glucose has the chemical formula C6H12O6. This is the molecular formula for it. That tells you how many carbons, how many hydrogens, how many oxygens are in glucose. Now, the empirical formula would be if we took this and we reduced it to the smallest integers that we could while maintaining the same ratio. This is 6 to 12 to 6, right? You could cut that in half and have 3 to 6 to 3, or you could do that even better, all the way down to 1 to 2 to 1. right? So the empirical formula for glucose is CH2O, 1 carbon, 2 hydrogens, 1 oxygen, okay? 1 to 2 to 1. Now, we can actually find the empirical formula for a substance based on percent composition, right? We were just doing percent composition. So if you look at this example problem, it says, example, the percentage by mass of a compound is 14.14% carbon, 2.38% hydrogen, and 83.4% chlorine. Calculate its empirical formula. So the trick to doing empirical formula problems based on percent composition is to first assume that you have 100 grams of the substance. If you assume that you have 100 grams of the substance, that turns the percentage values into grams, right? If you had 100 grams of something and it was 83% chlorine, that means 83 grams would be chlorine. So we can just treat these percentages as grams. 14.14 grams of carbon, 2.38 grams of hydrogen, and 83.48 grams of chlorine. So by assuming that we have 100 grams, the percents are now grams. All right, now step 2 is to turn the step 2 is to convert from grams to moles. Right? That means that you have to divide by the molar mass of each element. So I'm going to turn these grams of carbon into moles of carbon. 1 mole of carbon is some number of grams. I'm going to divide by the molar mass of carbon. On the periodic table, carbon is 12.01 grams per mole. Hydrogen, 1 mole of hydrogen is 1.01 grams. And chlorine, 1 mole of chlorine is 35.45 grams. So I'm converting each of them from grams into moles. Right? So 14.14 divided by 12.01, I get 1.177 moles of C. If I take 2.38 divided by 1.01, I get 2.356 moles of H. And if I take 83.48 divided by 35.45, I get 2.355 moles of chlorine. Now you should notice that these numbers are almost the exact same. Now it says the next step is it says use the numbers as subscripts for each element to express the ratio of atoms. So what we would have if we put these as subscripts, if I was writing a chemical formula, I have C 1.177, H 2.356, and Cl 2.355, right? Now you should recognize this is not how it goes, right? We never have these decimal points. We always have integers in terms of how many of each element we have. So we need to turn these decimals into integers. And the way to do that is to divide each of them by the smallest number. So I have some space on this here. I have, for carbon, we have 1.177 moles. For hydrogen, we have 2.356 moles. And for chlorine, we have 2.355 moles. Right? If I divide them all by the smallest number, watch what happens. The smallest number, this is the smallest one. If I divide this by 1.177, right? You divide that number by itself, that gives you 1. If I take this number and I divide it by 1.177, see what we get, right? If I take 2.356 divided by 1.177, I get this number, which is almost exactly 2, right? It's basically 2, right? We're going to have a little bit of rounding, but that's basically 2. And this is pretty much the same number as this. If I do this division, again, I get 2. So by dividing them all by the smallest one, it turns them into integers. That's 1 carbon, 2 hydrogens, and 2 chlorines. So our chemical formula is, or our empirical formula is CH2Cl2. 1 carbon, 2 hydrogens, 2 chlorines. That's our empirical formula. Pretty cool, right? These are fun. Kids usually like doing these empirical formula problems from percent composition. So let's do a couple more. So again, we have percent composition. The first thing we're going to do is turn them into grams. So we have 20.19 grams of magnesium. 1 mole of magnesium is 24.31 grams. I just looked on the periodic table for that. 26.64 grams of sulfur. 1 mole of sulfur is 32.07 grams. Again, that's the molar mass of sulfur, looking on the periodic table. And then I have 53.16 grams of oxygen. 1 mole of oxygen is 16 grams. So for each of these, I'm just dividing by the molar mass of that element on the periodic table. Okay, so 20.19 divided by 24.31, I get 0.8305. If I take 26.64 and divide it by 32.07, I get almost, look at that, almost the exact same number, 0.8307, I guess, if we're rounding, pretty much the same number. And then I have 53.16 divided by 16. That gives me 3.3, excuse me, 3.3-ish. These are moles, right? Mole, mole, mole. I need to turn them into integers, so I'm going to divide them all by the smallest one. So I divide by 0.8305, divide by 0.8305, divide by 0.8305. If I do that, this gives me 1, which is 1 magnesium. This gives me 1, which is 1 sulfur. And if we do this one, right, this number divided by 0.8305, we get a number which is almost exactly 4.0004 oxygens. So look at that. 1 magnesium, 1 sulfur, 4 oxygens. Right? If we're writing that out in terms of a chemical formula, that is MgSO4. Magnesium sulfate. Magnesium's +2, sulfate's -2. It's a neutral compound. Ta-da! That's our empirical formula. We'll do another. So this one just has 2, and this is actually a little bit of a different problem. I did this one on purpose so that you would see something else that happens sometimes. So we have 69.94 grams of iron, and we have 30.06 grams of oxygen. Okay, now 1 mole of iron, if you look on the periodic table, iron is 55.85 grams per mole, and 1 mole of oxygen is 16 grams per mole. So if we do each of these, 69.94 divided by 55.85, 1.252 moles, and then this one, 30.06 divided by 16, is 1.879 moles. All right, so now we need to turn these into integers, so I'm going to divide by the smallest one, divided by 1.252. That gives me 1 FE. And if I take this number divided by 1.252, what I get is, let's see, 1.879 divided by 1.252. 1.500. This is oxygens. Now, we divided by the smallest one, and look, it gives us 1 iron and 1.5 oxygens. If you get a half, you just take the whole thing. Instead of having, FeO 1.5, you can turn this into an integer by multiplying the whole thing by 2. If you do that, you get Fe2O3. That is still a 1 to 1.5 ratio. But we don't have these decimal points, we'd have integers. And that's what you have to do sometimes. If you get a 0.5, then you have to multiply by 2. If you got a point, let's say you got a 0.333 repeating, then you might need to multiply by 3. So sometimes that happens. You might need to be aware of that. That's why I wanted to do this as an example. Okay? Now, we've done percent composition, we've done empirical formulas, but I also want to show you that you can find a molecular formula from an empirical formula if you know the mass of it. Okay? And the idea here is the molecular formula is always the empirical formula times some multiple. Right? It's some multiple of the empirical formula. So if you know what the empirical formula is, and you know the mass of the molecular formula, you can find out how many times bigger the molecular formula is than the empirical formula. All you have to do is divide the molar mass of the molecular formula by the molar mass of the empirical formula. It will give you the number that you need to multiply the empirical formula by. So I think just doing examples is the easiest thing. It says, a substance has an empirical formula of CH2O. The molar mass, right, this is the molar mass of the empirical form, of the molecular formula, is 150.15 grams per mole. What is the molecular formula? So, the molar mass of the empirical formula, CH2O, carbon is 12.01, hydrogen is 1.01, and we have 2 of them, and oxygen is 16. So, if we add these all together, 1.01 times 2 is 2.02, plus this, that's 14.03, plus 16 gives you 30.03 grams per mole. So this is the molar mass of the empirical formula. The molar mass of the molecular formula is that. If you take the molar mass of the molecular formula and you divide it by the molar mass of the empirical formula, you will get some integer. Divide the molar mass of the molecular formula by the molar mass of the empirical formula. So 150.15 grams per mole divided by 30.03 grams per mole. If you do that, you get 5. Now, what does that mean? That means that the molecular formula is 5 times bigger than the empirical formula. So you're going to take your empirical formula, CH2O, and multiply it by 5. So that means instead of 1 carbon, now you're going to have 5 carbons. Instead of 2 hydrogens, now you're going to have 10 hydrogens. And instead of 1 oxygen, now you're going to have 5 oxygens. This is your molecular formula. And if you want to, you can add these up and see that the mass of this does add up. to 150.15. This is how you find the molecular formula, okay, from the empirical formula. So we'll do a couple of these, and then we'll be done for the day. It says, a substance has an empirical formula of CH3. The molar mass of the molecular formula is 30.08 grams per mole. What is the molecular formula? So CH3, that's 12.01 plus 1.01 times 3. So that's 3.03 plus this is 15.04 grams per mole. So the empirical formula weighs 15.04 grams per mole. The molecular formula weighs 30.08. You could probably see where this is going. If we take 30.08 grams per mole and we divide it by 15.04 grams per mole, we get 2. 2 is what we have to multiply the empirical formula by. So CH3 times 2 is, instead of 1 carbon, we're going to have 2 carbons, and instead of 3 hydrogens, we're going to have 6 hydrogens. And this is our molecular formula. One more example. I actually sort of did this by accident earlier in the lesson, but here it is. The substance has an empirical formula of C4H5N2O. The molar mass of the molecular formula is 194.22 grams per mole. What is the molecular formula? So C4H5N2O, if we add that all up, we find its molar mass, right? So 12.01 is carbon times 4, so that's our 4 carbons, plus we have 1.01, that's hydrogen, times 5, and then we have 2 nitrogens, so that's 14.01 times 2, and then we have oxygen, which is 16. So this whole thing has a molar mass of 97.11 grams per mole. Okay. Now the molecular formula has a mass of 194.22 grams per mole. If we divide that by 97.11 grams per mole, that gives us 2. 2 is what we have to multiply our empirical formula by, right? 2 times C4H5N2O. So instead of 4 carbons, we have 8 carbons. Instead of 5 hydrogens, we have 10 hydrogens. Instead of 2 nitrogens, we have 4 nitrogens, and instead of 1 oxygen, we have 2 oxygens. And this is a chemical formula that I used in an earlier problem, caffeine, and I sort of did this by accident ahead of time. But there it is, same thing, finding the molecular formula from the empirical formula. So we did a lot today. I know it's a lot of calculations, a lot of numbers, but we did practice problems with percent composition. That's finding what percent of a compound's mass is contributed by each element. And then we use percent composition values to find empirical formulas, and from empirical formulas, we found molecular formulas. Hopefully this has been helpful. Keep up the studying. Work. See you back in class.